share the screen. Here you can see our topic, half-wave rectifier, okay, diode application. Today we will be learning about rectification, and this will be a very important topic for your midterm, okay. Now let's start. Share a screen. See here. So half-wave rectifier diode application. So we will be learning about rectification today. What is rectification? Remember, rectification means fixing something, right? Fixing something. Rectification means fixing something. That means you have something that is not behaving well, so you will fix it so that it behaves well. Like your AC current. AC currents changes its direction frequently, right? 50 times in a second. Your AC current changes its direction 50 times in a second. That means it is going up, going down, going up, going down, right? So you do not want that. You want DC. DC means direct current. That means that is one-way current. You want your current to be flow in one direction, right? So that's why your rectification comes in. So I'm going to full screen this one. And you mute yourself, okay? All of you mute yourself. Okay, now, next. See this one. What is a rectifier? A rectifier is an electrical device that converts alternating current, that means AC current, which periodically reverse direction. Obviously, that is why that is called AC current, to direct current, that means to DC, which flows in only one direction. That means a circuit that converts AC to DC is called rectifier. Again, a circuit that converts AC to DC is called rectifier. Now, this is an AC wave, right? AC current, AC wave. So sometimes it is going up, sometimes it is going down, going up, going down, right? Periodically. So that's why this is called AC current or alternating current. Now we do not want that. We actually want one directional current. That means your current will remain in one direction, okay? Either in positive side or only in negative side. Not it will go positive, it will go negative, it will go positive, it will go negative. We do not want that. We want only one direction. That means either in positive or in negative. So what we can do, we actually delete this part, okay? We can delete this part. If we delete this part, that means this one, we can achieve the one directional current, right? So if we delete this part, this is one directional now. If we delete the negative portion of the wave, negative portion, that means this portion, we can get one directional, that means DC current, right? Or we can delete the upper portion as well. We keeping the negative part and deleting the upper portion, that is also doing your AC wave DC, okay? But actually our actual DC doesn't look like this. They actually look like these. That means a fixed value, this one. But we will see how to convert these to this, okay? We will see that. But at first, let's delete the negative portion, okay? That is how you can make your AC to DC. So your rectifier circuit can be divided into two parts. One is two types actually. One is half-wave rectifier. Another one is full-wave rectifier. The full-wave rectifier can be classified into two types. Number one is bridge full-wave rectifier, center-tapped full-wave rectifier. Bridge full-wave rectifier, center-tapped full-wave rectifier. So we will learn about all three of them, okay? But today's topic is half-wave rectifier. Now, what is half-wave rectifier? The process of removing one half from the input. one half in from one half the input signal to establish a DC level is called half-wave rectification. The process of removing one half the input signal to establish a DC level is called half-wave rectification, and the circuit is called half-wave rectifier. So if you remove one half, either the positive half or the negative half from the input signal to make it a DC, is called half-wave rectification, and the circuit who made this is called rectifier. This is a simple half-wave rectifier. Simple half-wave rectifier. You have one diode and you have one resistor. That's it. This will make your AC to DC. Okay, but remember, your resistor, that is this one, your resistor must be parallel with your output. So resistor is parallel with your output, and diode is series. Diode must be in series. Okay, now this is your VI where you will put your AC signal. This is your VO where you will get your DC signal, like this. If you give a AC signal, if you give an AC signal here, you will get a DC signal, like that. Okay, that means what is happening here? This circuit is actually cutting or deleting the lower portion or the negative half cycle. This is one cycle. The first part is called positive half cycle. Second part is called negative half cycle. Or you can say this is our first half cycle. This is our second half cycle. Okay. So it is actually keeping the positive and deleting the negative part. So that is how you can get it. Okay, but remember one thing. For the time being, for now, we will consider the ideal diode. No silicon, no germanium, no gallium arsenide. Ideal. That means we will think our diode will not take any voltage extra. Okay, it will not take 0.7, 0.3, 1.2. No, it will not take. So for understanding purpose or for discussion purpose, let's assume they are all ideal. They are not practical diode. They are not silicon, not germanium, not gallium arsenide. Okay, that means they will not eat any voltage. For now. Then we will consider about silicon. Now, how half-wave rectifier get this value or get this waveform? How we can get these? Okay, let's discuss about that. So first we will consider about first half cycle. That means the positive half cycle. We will consider about first half cycle or the positive half cycle. That means this one. That means this part. Okay, only this part. We will consider about this part first. Then we will consider this one. Okay, first half cycle. So in the first half cycle, remember, this is your plus, this is your minus. So current will try to go in this way, right? Like this. Current will try to go in this way. Remember, current will try to go clockwise, right? Since it is going clockwise, so your diode is forward bias because current is going from plus to minus, right? So that's why your diode is forward bias. When your diode is forward bias, it will allow the current to pass. It will allow the current will pass. That means it will be short. It will act like a short, like this. It will act like a short. That means current is going, current is passing. If current is passing, all the resistor, that means you have only one resistor, right? So whatever voltage you are giving here, whatever voltage you are giving in the input, you will get the exact same output. Because if you had two resistors, then your voltage would have been divided according to the voltage divider rule. If you had two resistors, that means let's say R1, R2 or R1, R2, that time your voltage could have been divided, could have been. But since you have only one resistor, that means all the voltage, what you are giving, that will go and, what is that? That will go and, what should I say? What is the word? that will go and accumulate it on the resistor. That means whatever you are giving, you will get the exact same voltage, right? If you give 5 volt, you will get 5 volt. If you get 10 volt, you will get 10 volt. If you give AC, you will get AC. That if you give first half cycle, you will get first half cycle. That's it. So you are giving first half cycle as input, you will get the first half cycle as the output. That means your VO should be equal to VI. That means this one. Because your first half cycle was this one. So this part was your input. So you will get this part as your output. Okay, exact same amount, nothing will be lost, exact same amount. Now for the second half cycle, that means we will be talking about this part as your input, because for these we already get these, right? Now we will consider this part and let's say whether we get 0 or not. Okay, let's see. For second half cycle, remember your plus is here and your minus is here, because alternating current. Alternating current means for first half cycle current goes like this, for second half cycle current goes like this, right? In circuit, for first half cycle current goes like this, for second half cycle current goes like this, right? So they changes the direction. Since for second half cycle they change their direction, so this is the plus, this is the minus. So current will try to go like this, like that means anti-clockwise, like this. So current will try to go like this. Understand? Okay. Now what will happen? Since current is going from this point to this point, that happening to my internet. Okay, so I'm facing a lot of problem today. So did you hear what I said?
Yes, sir.
Okay, I will give you the recording. Okay, you do not worry. Do not worry.
Okay, sir.
Okay. Share screen again.
Do you hear what I'm saying right now? No.
Okay, now see, everyone. So since current is going in opposite direction, that means the diode is reverse bias. And as you know, in reverse bias, there is no current flow, right? There is no current flow. That means we can say this is an open circuit. Open circuit means no current flow, right? Since there is no current flow, so resistor will not get any voltage, because we know resistor will get voltage if there is a current flow. Since there is no current flow, no voltage will be dropped here, right? No voltage. That means your output will be 0. 0 means like this. So this part. So this is the part we already got when we had first half cycle. So this is the part we got. Okay, mute yourself. Please mute yourself.
If you believe the word Malcolm, the woman, I mean, because you are not that. I know you have. Hello? أذكر.
Okay, you are muted, right? Now, see, so this part we already got for first half cycle, and this part, that means the 0 part, we got for second half cycle. So if we think for 2 cycles, see, first half cycle is fine, this one. But for second half cycle, it becomes 0. Again, For first half cycle, it is fine. For second half cycle, it is 0. Remember, for this, our VDC, that means the DC level, is 0 volt. Why? Because if you make them average, you will get 0. Average means what? So because this is plus, this is minus, this is plus, this is minus, so they cancel each other. So you will get 0 volt. But if you make them average, if you take average area of this part, right? Your voltage will be 0.318 into Vm. That Vm is the highest value. How I am getting this? This is actually a geometrical term, okay? The area. Here you can see the area of this part is equal to the area of this part. Area of this part equal to area of this part. So if you take average area, remember this plus this minus this, because they are negative. So that's why they will be minus. So this minus this plus this minus this. So eventually they will become 0. So that is your DC. But for this, there is no minus. So this plus 0, this plus 0. So if you divide, this will be your answer. Okay, this is an average area. If you take an average area, 0.318 into Vm will be your answer. So that is called DC level. That is the DC level. Remember this word, DC level. Okay, so if I tell you to find the DC level, so you have to use this formula. VDC is equal to 0.318 into Vm. What is Vm? Vm is the actual, not actual. Vm is the highest value of your output. Okay, Vm is the highest value of your output. So if it is 10 volt, it will be multiplied with 10. That means 0.318 into 10. If it is 20, it will be 0.318 into 20. If it is 19.3, it will be 0.318 into 19.3. That's it. Now come to the next one. Okay, the formula is 0.318 into Vm. Now, what will happen if we consider the silicon diode? What will happen? What will happen if we consider the silicon diode? Right? Like this. If you consider a silicon diode, it will no longer be short. Remember, you will have a voltage drop here, right? The voltage drop, let's say the voltage drop is Vk. Let's say the voltage drop is Vk. For silicon, it is 0.7. For germanium, it is 0.3. For gallium arsenide, it is 1.2. We all know that. So when there is a drop, what will happen? So your 20 volt, from your 20 volt, 0.7 is gone. So how much your resistor will get? Rest of it, right? From 20 volt, let's say for 20 volt, from 20 volt, 0.7 volt is gone. How much your resistor will get? Rest of it.
Sir, we can't hear you.
So can I continue?
Yes, sir.
Okay, now you can hear me? Okay. Okay, I'm going to do one thing. I'm going to mute participant. Okay. That's it. Again, so when we deal with the practical diode, that means silicon, germanium, gallium arsenide, that time you will have a drop here, right? Let's call the drop is Vk. So when your input is 20 volt, let's say 20, that time your 0.7 volt will be gone, right? For silicon diode, this is gone. So you cannot do anything else here. So this will be gone. So how much your resistor will get? Your resistor will get the rest of the voltage. That means if you have 20 volt here and 0.7 is gone, rest of the voltage, that means 19.3 will be your output. If you give 10 volt, 0.7 is gone. So rest of it, that means 9.3, you will get as your output. So as you can see, your input was bigger. Your output is a bit smaller. How much smaller? By Vk. So your highest value will be Vm minus Vk. So 20 minus 0.7, that means 19.3. That will be your highest value. Vm minus Vk. So what will be the DC level now? Previously your DC level was this one. So here the highest value was Vm. That's why your DC level was 0.318 into Vm. Okay, 0.318 into Vm, because your highest value was Vm. Now your highest value is Vm minus Vk. So what will be your formula? Your formula is 0.318 Vm minus Vk. This one. Okay. So what is Vk? Vk is 0.7, 0.3, 1.2, depending on the diode you are using. Now let's do one example. Sketch the output. Sketch means to draw. It sketches the output VO and determine the DC level of the output. That means that from the formula, VDC is equal to 0.318 into Vm. Repeat part A if the diode, if the ideal diode is replaced by a silicon diode. So you have to do the part A, that means the sketch the output VO and determine the DC level of the output. If a silicon diode is applied, that means the first part, the diode was ideal diode. That means no silicon, no germanium, no gallium arsenide. Normal practical diode. No, not practical diode. Ideal diode. Second part, that means B, is a practical diode. That means a silicon diode. Part C, repeat part A and B if Vm is increased to 200 volt. That means for part A and part B, the voltage was 20 volt. Now you have to repeat the part for 200 volt. That's it. So let's see. So this is your circuit. As you can see, your diode is reverse, right? Your diode is opposite, not the previous one. It is opposite. It can be there. It can be there. And your input is 20 volt and minus 20 volt. That's it. Now let's analyze. Okay, let's analyze. So remember, for first half cycle, this is the solution A. For first half cycle, wait a minute. For first half cycle, that means this one, 20 and minus 20, right? For first half cycle is 20, this one. This is your plus, this is your minus. So current will try to go in this way, right? Clockwise. Current will try to go clockwise. But remember, your diode is reverse bias now. Why? See, for first half cycle, current will try to go in this way, right? Clockwise, like this. But can it go? No, because your diode is reverse. Diode is blocking that. Okay. So that time, what will happen? This short circuit will become open now. So no current can go. If there is no current can go, so your output will be 0. So for that, your output is what? 0. For negative half cycle, that means when this is plus, this is minus, current is trying to go in this way, that means the anti-clockwise. That time, the diode is forward bias and diode becomes short. When the diode becomes short, that time, what will happen? Your resistor will have some voltage. How much volt? Whatever the input, that means the negative half cycle, whatever the input you will have the exact same output. Okay? That means this circuit is taking away your positive cycles, positive half cycles, but giving away the negative half cycle. That means your positive half cycles are gone but your negative half cycles are there. Remember, we made one formula from there. What was the formula? The formula was VDC 0.318 into VM. So this formula was created for positive half cycle, right? For negative half cycle, that means when you have only negative half cycle, not the positive half cycle, that time you have to give a minus in front of it. Either you give a minus here or you give a minus here, okay? Minus VM. Remember. Okay. Now the formula. So VDC is equal to 0.318 VM. Obviously, you can give a minus in front of it, or you can give a minus in front of that. So which one I like? I personally like giving a minus in front of 0.318. I personally like, but I haven't shown here yet. I will show that later. Okay. So remember, when your output is only positive, you give positive. When your output is only negative, that time you give a negative. Okay. So here I give the negative in front of 20, but you should give the minus in front of 0.318. Okay. Obviously, the minus will go in front of 0.318 eventually. Okay. So here 0.318 into VM, 0.318 into minus 20, that become minus 6.36 volt. Solution B. If you apply a silicon diode here, what will happen? For silicon diode, your VM minus VK will be there. VM minus VK. 0.318, VM is minus 20 and VK is 0.7, right? So you should have minus 6.5826, but this is wrong. Why? Because remember, see this, it was minus 20, this is 0.7, they become minus 20.7. So they increased, right? This should not be the case. This minus indicates the direction, and this minus indicates the reduction. This minus indicates the direction, this minus indicates the reduction. But how other people will know? They will not know. Only I know this is for direction, this is for reduction. Only I know it, or you know it. So that's why our answer is wrong. That's why I told you to use minus in front of 0.318 instead of VM. Okay, let's see. Here, what you can do, you do not minus them. You already minus in front of your head, or you make a minus inside your head, then give a minus in front of it. Okay, so it is 20. Obviously, it is minus 20, but minus is for direction. So it is 20 and minus 0.7, that means 19.3. So this will be minus for direction, and the answer is 6.1374. An ideal way. Wait a minute. Okay, the actual way of doing it, or the more perfect way of doing it, is this one. VDC. So you put a minus in front of 0.318 because you know it is negative half cycle. So you put a minus. When it is positive half cycle, put a plus. When it is negative half cycle, put a minus. Minus 0.318 VM minus VK. The VM is 20 volt and VK is 0.7. That gives you minus 6.1374. They are exact same result, but this is much easier to understand. Okay, you use this. Now for part C, what is your part C? Part C is repeat part A and B if VM is increased to 200 volt. Now this value is 20 volt. So we will do the part for 200 volt. part C. So again, for ideal diode, for part A, this is part A, right? We are repeating part A. For ideal diode, your VM is minus 200. Obviously, you can put the minus in front of 0.318, and you should put the minus in front of 0.318, right? That is the actual, that will be more appropriate. 0.318 into VM, 0.318 into minus 200, or you should put the minus in front. That means minus 63.6 volt. That is when you use ideal diode. Now put actual silicon diode. So if okay, I do not want you to do this. I want you to do this. Do this. Okay. Do not do that. Do this. Okay. VDC is minus 0.318. VM minus VK. Your VM is 200 and your VK is 0.7. So 200 minus 0.7, that is 199.3. And since there is a minus in front of it, so your value will be minus 63.3774 volt. Okay, that's your answer. Now, PIV. What is PIV? So this is a rating. You have to understand about your diodes. PIV, that means peak inverse voltage, or PRV, that is peak reverse voltage. Those are the ratings of your diode is for your design. You have to make sure your diode will not sustain, or your diode will not face more voltage than your rating. What do I mean by that? Let's say your silicon diode can sustain. Do you understand sustain? Sustain means it can hold, or it can work with, it can cope. Okay, your silicon diode can sustain a maximum amount of voltage of 50 volt. That means if you give more than 50 volt, your silicon diode will be damaged. Okay, let's say your diode can hold, or your diode can work with maximum 50 volt. That means if you give more than 50 volt in reverse bias, your diode will be damaged. Okay, that time you cannot give more than 50 volt. So that 50 volt is your PIV or PRV. That means peak inverse voltage or peak reverse voltage. So whenever you are making some design, you cannot apply 50 volt or more than 50 volt. Okay, what do I mean by that? Let's go back to the example. In this example, we have done the math for two different voltages, right? One voltage is 20 volt and part C was 200 volt, right? So 20 volt and 200 volt. For 20 volt, your PIV must be more than 20. That means your diode must sustain. Your diode must work with 20 volt, or your diode must hold 20 volt. But for 200 volt, your PIV should be more than or equal to 200 volt. Because if your diode cannot sustain 200 volt, your output will not be there. There will be no output. Okay? There will be no rectification. Remember, there will be no DC. Understood? Because your diode is damaged. Whenever you put it there, it will be damaged. Your diode can hold 50 volt and you are using 200 volt. That time, instantly your diode is damaged. If your diode is damaged, your rectification is gone. You are no longer getting DC. You are getting AC. Okay? Your rectification, your converter is damaged. So that is called PIV. So before designing, you must understand what is the PIV rating, and you should use PIV more than your required voltage. So your PIV should be more than, equal or more than VM for half-wave rectifier. Now, remember at the first slide I told you we will flat the curve. We will make the curve flatter. Okay, let's go back and see. Remember I told you? So we will make the curve like this. We will make the curve from this to this, right? We told you. We told you before, right? I told you before. Now see, I will show you now how we can make this to this, okay? We have to use a capacitor. We have to use a capacitor filter to flattening the curve. Effect of capacitor filter. See, what is a capacitor filter? We have to add one capacitor with parallel to your resistor. Parallel to your resistor. Remember, if we apply a capacitor with parallel to resistor, what will happen? This will happen. So this is half-wave rectified output. That means your negative portion is gone. Positive portion is there, but negative portion is gone. So if this is for no capacitor, when we do not have any capacitor, that and this is your result. When we apply capacitors, your pink color, this pink color lines, these are actually your outputs. Now when we apply a small capacitor like 1 microfarad, that time this will be your result. So this is becoming flatter, right? When we apply 2.2, it become more flat. When you apply 10, it become more flat. When you apply 22, it become more flat. It is not going up and going down, not like that. It is flat. When you apply 100, it is even flatter, right? So this is how you can flat your DC signal. Now, this portion is, we got it from simulation. We got it from simulation, right? Now I want you to see some result from oscilloscope. That is from your lab. I got this from your lab, okay? And I'm showing you this. I got this screenshot from your lab. This is actual screenshot. Actual, that means this is the output of actual circuit. Actual circuit, that means the circuit is made in the breadboard, and then I took the result from the, what is that? From the oscilloscope. This is the oscilloscope result, the actual result. Not computer result, this is actual result. So this is your full wave, AC wave, right? And this is your rectified, half-wave rectified result. No capacitor. Okay. Now if we apply capacitor, see your curve is flattening. This is for 1 microfarad. This is for 2.2 microfarad. It is more flattening. If we apply more, it is 4.7 microfarad. I forgot, maybe 22, not 4.4. It is 22 microfarad. This is 47 microfarad. Okay. This is 100 microfarad. This is 200 microfarad. So as you can see, no capacitor, capacitor, more capacitor, more capacitor, more capacitor, more capacitor, more capacitor. So if we use bigger capacitor, your curve will be flatter. But I believe you should use anything below 100, not more than 100. Okay, anything below 100, not more than 100. Why? Because as you can see, your highest value here is 14.4. Can you see that? Your output value is 14.4. It is 14.4. For these 14.4. For these it is 14.4. For these it is 14.4, 14.4. For 100, it is also 14.4. But whenever we use more than 100, that means 220, it becomes flatter, but the voltage reduces. 14.0. That's why we should not use more than 100. Anything 100 is anything around 100 is enough. Understood? So that's all. That's all for today. Okay. Exit. That's all for today. We will not learn anything more today. Okay. I'm going to stop the recording.